Okay, first speaker is going to be Jepsen. He's going to tell us about challenges to accumulation point.
Yes, thank you so much. Good morning, everyone, and allow me to start off by thanking the organizers for putting together such a wonderful conference. But let me also thank each one of you for showing up here on a Saturday morning to attend my talk. Yes, so indeed this talk will be focusing on these accumulation point amplitudes, and so by this I mean string theory candidate tree amplitudes that possess this property that they have an infinite sequence of poles, or semi-infinite sequence, but one where this sequence now converges on an accumulation point at some finite value of center of mass energy, right? And these amplitudes they've seen a good deal of interest in these past few years, and there have also been some sort of generalizations of them. And an additional curious property is that they possess a branch cut, even though they're candidate tree amplitudes. And perhaps a comment on nomenclature. I see David Gross is not in the audience. I hope you'll bear with me. Sometimes I might just use the word amplitude instead of candidate amplitude, right? So here's what the reggae trajectories look like. You'll notice instead of having the usual linear ones that are familiar to us, they bend and approach then this. So this is the value where you'd have S infinity. And then from this value, the branch cut emanates. Yeah. And so it's not known. So this is why I was talking about candidate amplitudes, right? There's no known physical theory by which you can derive these amplitudes. And it's also, they've passed some number of unitarity checks, but those checks have not been exhaustive. So the problem of exactly what to make of them is still an open problem. But of course, it would be nice to resolve, if we really hope to carve out, the space of unitary S matrices and string theory amplitudes in particular, right? We would like to know where exactly, if at all, these accumulation point amplitudes fit into the picture, right? So the Kuhn amplitude, that was like the first one. So sometimes I'll just refer to the Kuhn amplitude, or sometimes the Kuhn amplitude and its generalizations. So okay, here's what the Kuhn amplitude itself looks like in the formulas originally written down. Just a single year after Veneziano wrote his amplitude down, right? So it's given by this infinite product, and it's symmetric in S and T, and so it's conveniently expressed in terms of sigma and tau. And now let me start off by noticing I'm using a slightly different notation than Grant was using in his talk, right? So he was roughly what he called sigma and tau is the logarithm of mine. But since I'm going to allow these to assume negative values, that notation is not as convenient in this case. And also this sigma and tau, they're going to appear in basically every single slide. So maybe I should just write them down here. Right. So just in case you're forgetting. But I mean, loosely speaking, you can just think of sigma and tau as S and T. So they're just linear or anti-linear functions of the Mendel sum invariance. Okay, and so then we have this parameter Q. So that's some real number, a real continuous number between 0 and 1. Okay. And so the number of parameters, so the Kuhn amplitude, it's a function of two variables, S and T, but it has three parameters. So two parameters enter directly. We have Q, and then we have the mass squared. And then indirectly, it depends on the number of space-time dimensions in the ambient space-time if we attempt to do a partial wave decomposition. So okay, so let's look at the poles of this amplitude. We can read them off directly just from the denominator, right? And so it's a simple exercise. Right? I mean, you can see you have a pole when sigma is an integer, non-negative integer power of q. Just from the definition of sigma, a simple exercise, you derive that these are the values where you have the poles, right? And so they're spaced according to what are called the Q integers, right? So this is a generalization of the integers, which when Q goes to 1, this nth Q integer just goes to n. But when Q is less than 1, then they approach a finite value where this term just drops away, right? And so that means we have this accumulation point where the S channel poles converge on. And so in principle, in this first form, the Kuhn amplitude actually has non-polynomial residues, right? And this is usually something we don't want, right? Like because on a pole, right, we have some exchange of particles, and we prefer that to be a finite number of spins being exchanged, right? Otherwise, if you have an infinitely many number of spins, right, then somehow would require you to have an infinitely extended object, right? To not have some infinite deformation in a finite region. But so yeah, basically just by canceling factors between numerator and denominator, you see that actually in the original form it's polynomial in 1 over tau instead of being polynomial in t, right? But so Kuhn and collaborators they found a fix to this where they introduced this extra prefactor. So the prefactor it's symmetric in S and T. Then it has this property that you can just check, right? That when you evaluate it on a pole, so you set sigma equal to a power of q, then this itself becomes a power of tau, precisely such that this becomes a polynomial, goes from being a polynomial in 1 over tau to being a polynomial in tau and t. Okay. And then yeah, so I refer to this as like a deformation of the Veneziano amplitude, right? So in the limit when q goes to 1, you recover the familiar Veneziano amplitude. And perhaps I can one possible question you might have, which I can sort of preempt, right, is that why would you introduce this factor? Why not just change sigma and tau to 1 over sigma and 1 over tau, right? That would be an alternative fix. And the reason you don't do that is that you can very quickly check that if you do that, then you get the partial wave decomposition. You get negative partial wave coefficients, right? So that's you can very quickly see that's non-unitary. So that's why instead you introduce this factor, but it comes at a certain price because basically this prefactor is what gives the amplitude its branch cut, right? Which is gonna play a big role in today's talk. Okay. And now just a little maybe a bit of an aside is that you can also express the amplitude in terms of the so-called Q-deformed gamma function. And that's another way to understand how it has the nice residues, right? It's because just like the usual gamma function, it has sort of a nice recursive property, and it also has poles at the non-positive integers. Yeah, it's to the best of my knowledge, these two UCLA grad students who first wrote it down in terms of these Q gamma functions. Now, there was this work here by Simon Kahnhuro, Sohako Magotsky, Amit Sever, and Sasha Siboyedov that basically under pretty mild assumptions, the string theory amplitudes you can get, or more precisely, the only amplitudes with spins greater than 2, they will necessarily have to tend to the Veneziano amplitude, at least in this limit when S and T is large. Okay, but the Kuhn amplitude is and its generalizations. They're examples that do not meet the assumptions that go into this theorem. I mean, because they're non-meromorphic, right? But both by having an accumulation point and by having a branch cut. But it was pointed out that they do satisfy the positivity conditions on the poles that you would expect from unitarity. And so over sort of the last year and a half, there were several authors who started looking more closely into these positivity conditions and sort of chart out in the space of Q and M and D, charting out what the space where the positivity is satisfied on the poles. And also you can check the Wilson coefficients are compatible with causality. And then it's been known since the very beginning, right? It has the sort of the nice benign high energy behavior that we want for string theory amplitudes, in the limit of large S and T, and also in the fixed large absolute value of S, like large center of mass energy, both Regge limit and fixed scattering angle limits. Okay, and then finally over this past year, there have been a number of proposed generalizations, both some discrete generalizations that sort of shift around the locations of the poles and the first, like how the spins lie according to on the first poles, but then also these continuous generalization that Grant Remen told us about in his nice talk on Wednesday. And let me also just clarify that this talk only applies to these amplitudes that have a Q in them, that have this accumulation point spectrum, right? Because Grant talked also about like a version that just has an R, right? So that still has the usual Veneziano poles. So my talk has no bearing on that proposal. All right, yeah. So the open question remains, what exactly we're to make of these amplitude, right? And we also heard in his talk on Wednesday, they suggested one possible picture for how they could arise in terms of amplitudes on d-branes in AVS. So at least one thing that's noticeable is that these proposals and generalizations, these accumulation point generalizations, have only been proposed for as deformations of Veneziano. There's like the authors specifically state that they didn't find them for Via Shapiro. Right, so it seems like, oh, possibly the string endpoints might play some key role indeed, because people haven't been able to deform fine generalizations of the closed string amplitudes. Okay, but yeah, also the other question that was sort of open was if the amplitudes also satisfy the positivity conditions that must be satisfied for the branch cut, right? So for the rest of the talk, that's what we'll look into. So we'll perform this additional check. So let's just take a brief recap of what exactly are these positivity conditions I'm talking about, right? So of course, yeah, we're all familiar with unitarity, and then in this case, because we're now dealing with what I proposed as just perturbative amplitudes, right? Sort of leading amplitude in the perturbative expansion, right? That means that all we can get, right, once we go into this diagonal basis in terms of partial waves that you use Gegenbaum polynomials. So for that, this right-hand side is I mean, it's an absolute square, so it's positive, right? Like we can't say any more than positive because we're just doing perturbation theory. Okay? But yeah, the upshot is just, whenever we have an imaginary part, that has to be related, and that has to decompose into something that's positively weighted. And so yeah, here again, if a reminder of what the Kuhn amplitude itself looks like, right? And then we pick up an imaginary piece both on the poles, that's just arising from the I epsilon description due to this distributional identity. But then this extra factor, right? Like there are several ways we can write it. But basically, if we think of it as sigma raised to some power, which, for generic values of tau is not going to be an integer, right? Then it's clear enough that this expression here itself has a branch cut for negative, when either negative sigma or negative tau, right? So that gives us an extra imaginary discontinuity, right? And so decomposing these imaginary pieces into partial waves, we want the coefficients to be positive, right? And so in principle, if you just looking at the poles of an amplitude, you're in a sense only looking at a measure zero subset of the total set of conditions, right? Because this is just a discrete number of conditions. Whereas on the branch cut, right, it's sort of a continuous function you have to check. Plus also, the sum over spins can extend to infinity. Right, but so before looking at the branch cut, let me just, first both providing just a slight caveat, right? Because in principle, unitarity applies to the full amplitude, right? So, and yet nonetheless, so far we've just been looking at a partial amplitude, right? It's a function that's, symmetric with respect to S and T. Right? So usually, like in Veneziano's first paper, right? Yeah, you add them all three together. But the Veneziano amplitude itself satisfies positivity already at the level of the partial amplitude. Right, and so I mean, in a sense, that's why you can put Shan pattern factors at the end of the string endpoints, right? Because the unitarity doesn't rely on a subtle cancellation; they are unitary separately. So that's the same case, for the Kuhn amplitude. People assume it exists already at the level of the partial amplitude. And so, okay, I just 2 slides to sort of summarize what are the constrained, what are the allowed regions from the poles. Yes. This one? Well, I mean, I guess you can say it's an empirical observation in the case of Veneziano, say. So, right, but, I mean, you said 14 you can, yeah. So maybe it's sort of a disclaimer that there, if now I start to point out some violations of positivity, this might be a possible loophole. But at least it's not a loophole that's realized for any of the other string theory amplitudes we know. Right. Yeah. Right. Right. Yeah. Oh, yeah. And so for the Kuhn amplitude, so what usually happens, right, is that you get the strongest unitarity constraints just looking at, usually it's just from the first residues, right? So for example, you get the critical dimension 26, right, just by looking at the first non-constant residue of the Veneziano amplitude, or d equals to 10, the same thing for the super amplitude. And so in the case of the Kuhns, these are the 2 bounds. These are the 2 first the 2 first coefficients you get in this partial wave expansion. And so from that we get these bounds on the mass squared. Okay, but then so in principle this expression here, right, Q is between 0 and 1, right? But in general, this left-hand side is less than -1. And usually the literature hasn't really looked at the regime where the mass is less than -1. Like it's kind of an exotic regime because you would have multiple tachyons. But basically, okay, so basically it's just the point is that so just the two residues we just looked at, they give us these two bounds. They give us an upper and a lower bound on the mass squared as a function of Q, right? And then basically what this paper showed was that so they had an analytic proof that in this regime here that there's sort of a curve, and on the left-hand side, the positivity conditions are satisfied on all the poles in any number of dimensions. And then in this regime, it's satisfied only below a certain critical dimension. That's going to depend on where you're located in this region, right? So I stole this figure from them. Okay. So basically, this is the space of allowed regions we have left. In principle, also the purple region. And now, so what we're going to do now is now we're going to see, okay, but what's left now once we start looking at the branch cut? Okay. Right. So yeah, here just, a simple exercise just to write down what the branch cut is equal to. And now it turns out like you could just try sort of, do some like quick numeric checks. And I'm sure people did this, and indeed it does look positive. But it's going to turn out there are some like very well concealed numerical effects. And so for this reason, it will be advantageous to try and look at this from two different angles, both trying to get sort of a partial analytical handle, and also to try and flesh out what is the region where what is the region that most severely restricts the allowed values of the parameter space. And yeah, so we're going to look both at the forward limit, and then having some idea of where to look, then we'll perform some brute force numerical checks. So okay, if we start with just analyzing the forward limit, right? And so the idea here is that these partial wave coefficients, right? Like sorry, the partial waves and their coefficients. So written in terms of theta here it's the scattering angle in the center of mass frame, right? So the point is that just simple as like a mathematical property of these functions, right? If you evaluate them at unit argument, then these polynomials and any number of derivatives will be non-negative, right? So that means that similarly, if we were to differentiate this expression here with respect to cosine, right, any number of times, and then evaluating at cosine theta equals to 1, that's to say the forward limit. So that's also when chi is 0. If we do that, then we still should get something positive, assuming unitarity, right? If these coefficients themselves are non-negative, right? And then, so in principle, we'd have to differentiate the discontinuity with respect to theta, right? And then, just we pick up, just the chain rule, this extra factor. But you can just check, right? Both because we want to be situated on the branch cut, and also we want to assume unitarity, right? So we're going to, we had this constraint from the pole. So on those constraints, this thing will automatically, this extra prefactor will be positive. So really, this is just what we have to check. Yes. So, but there's sort of a zeroth order question you have to ask first, right? So the point is, before we even ask if we have, these positive coefficients, we should ask if this discontinuity, this imaginary if we even have just a purely imaginary discontinuity. And so the issue is that actually this version of the Kuhn amplitude has a double branch cut, right? In the sense that you run into trouble when both sigma and tau are negative. Then you start to get something that's not just imaginary but complex. And that in itself could be an issue, but it certainly is an issue if that happens in the forward limit, right? So the very first thing we have to just impose is that in the forward limit we want tau to be non-negative. Okay, and that gives us this constraint, which in principle, depending on the value of Q, already restrains a bit the region, the allowed region we looked at already. But okay, so now we move on. So just you can just look at this discontinuity itself and see when it's positive. That's a fairly simple exercise, right? Because the overall sign is determined by this sign function, and also by this factor here, this factor in the denominator. And in principle, they both change signs when you have when tau is a positive integer of n, but when tau is a negative integer of n, then this sign function starts to change sign, and that means it's, and so this one is going to flip back and forth between positive and negative and give you some forbidden regions, right? And so these conditions on tau, once we take the forward limit, we can translate those into conditions of the mass as a function of Q. Okay, and so just plotting it's going to look like this, right? So these are the forbidden bands I just told you about. The purple region, that's the region where we have tau, where tau is negative in the forward limit, right? That's like this complex region that we don't want. But basically, if you look, the dotted blue lines here, those are the upper and lower bounds we got from the poles, right? Then pretty much everything is still allowed, at least in the regime of masses that the papers were focusing on. So nothing has been forbidden. Okay, but now once you take a derivative, yeah. So yes, that's right. So in principle, you also have the tachyon-free strip here between the x-axis and the dotted blue line. That's right. So Q going to 1, then the Veneziano amplitude sits right here at this corner. So what was the question? Yes. Oh, I am allowing for tachyons. Yeah. I'm taking the Veneziano to be okay, as just being, you're not sitting at the minimum of a potential. Yes, at least from just looking at the poles, yeah, it appears, right, that once Q increases the allowed values, yeah, you get more allowed values. That's true. But now we're looking at the branch cut, so then this might change. And in fact, I can reveal it will. But yeah, basically, just we all know how to differentiate. This is what you get, and this basically just looking directly at the derivative, it's kind of hard to see if it satisfies positivity or not. Basically, the regions is that you have this cotangent function, but also these Q-deformed digamma functions appearing. Like, it's not surprising you get Q digamma functions because you're differentiating Q gamma functions. But the point is, in a sense, right? Like so for example, if we just look at the gamma function itself, right? It's at positive arguments, it's very well behaved. It's smooth. Its derivatives are smooth and monotonic, right? It's just a factorial function. But for negative arguments, it keeps flipping sign. So really, what we'd like to do is we'd like to flip, we'd like to flip these functions to the regime where they're nice. So basically, what we need to use is a Q analog of Euler's reflection formula, allowing us to switch between positive and negative arguments. And that comes at the price of introducing these extra functions, which are basically like these Weierstrass quasi-periodic functions. So the reason elliptic functions appear is basically, when we have these arguments appearing inside an exponent of Q, which means in principle, if you look at this factor, it's going to be periodic in the imaginary direction with periodicity 2 pi over log Q. Right, so that's why we start to get this second periodicity and why elliptic functions appear. Okay. But it just happens that then when you flip, you use this reflection formula, you get sort of a cotangent, which is just that's the same you'd get for the usual gamma function. But suddenly you also get these extra terms, these extra sinusoidal terms, which have coefficients that are actually extremely strongly suppressed in Q. Right. So if Q is some number of order 1. Right, then you get these tiny coefficients that are like multiplying with sinusoidal functions. Okay, and it turns out that these functions are actually going to be the main key players in the story, right? And so sort of a reason why you have this unnatural smallness is basically you have sort of a modular relation, right? I mentioned elliptic functions, right? So this is sort of looking in the case of a rectangular lattice. This is sort of swapping the x and y axis. And so that you have a relationship basically between Q gammas and Q prime gammas with this relationship between Q and Q prime. And so, if Q is greater than something like 0.002, right, then 1 will dominate much over the other. Okay, but so basically, yeah, just using this identity, we get now nice smooth functions, the analog of having the gamma function at positive arguments, right? But then we have these additional sinusoidal terms. Okay, and what we can see already from this expression is that, we want the right-hand side to be positive. And so to get the sharpest bounds, basically we need to take the limit where absolute value of sigma goes to 0. So we need to take the limit. So basically the positivity constraints are the sharpest if we go to the branch cut and we go all the way down right at the accumulation point. And then the dependency on sigma will just be via this in this periodic manner. Okay. And so then, okay, so let's just plot now what are the allowed regions. So the point is, when Q is very small, then these coefficients I showed you, they start to matter. And actually it becomes negative for any value of Q, right? And so in principle, for small values of Q now, like there's no value where the Kuhn amplitude satisfies the positivity conditions. So this was, so looking just at the first derivative. But now the point is, once we start to take more and more derivatives, we sort of this terms we sort of get more and more rid of this term, whereas the sine functions, they just keep flipping between cosine, cosine, and sine. So basically, you start ruling out more and more and more the more derivatives you take. And so in principle here, it's like it got a bit, the functions involved got very complicated, and also to go to the required numerical accuracy to reliably see what's allowed. So eventually I had to stop after 8 derivatives. So you might hope that there might be some remaining region that's allowed, but yeah, so we can address that now using the other method. And so the idea here is that we can also get these coefficients just by using just through numerical integration, because of just using these Gegenbauers. They satisfy they have this orthonormality relation, right? So you can just multiply the discontinuity with a Gegenbauer, and then you integrate to single out a coefficient, right? But then now we've learned that the regime where positivity might be violated is the region right above the branch cut, right? So basically, the idea is that we want to use then for this discontinuity, we look at the asymptotic regime where the dependency on sigma up to some overall function is going to be this periodic behavior. Okay, so basically, what happens when you compute these Gegenbauer coefficients is that they start out positive, as you'd hope for, but eventually they become small enough that you start to see these sinusoidal terms, right? And as you go higher and higher in the spin you look at, eventually these coefficients start to dip into negative values, and so the positivity is violated. Okay, and now so the example I just showed you now, right? That is a general behavior you see, across different values of m squared and q and d. You start positive in order 1, but eventually you start to see the sinusoidal terms, and eventually you get negativity. Although sometimes, right, the greater q is, the higher you have to go in checking these partial wave coefficients before you see the negativity. But eventually, all the examples that you can try and look at least in my case, you see the negativity appearing. All right, so since I'm running out of time, let me just provide a brief summary and outlook. In fact, the summary is quite simple, that the Kuhn amplitude in its current form doesn't satisfy the positivity conditions we would expect from unitarity. Right, so this seems to present some challenge to the picture where you have some smooth, continuous family of amplitudes that interpolate between like scalar amplitudes and the Veneziano amplitude. Yeah, and so like the worst case scenario, you could just say that, like, I mean, it's not unfamiliar, right? That like once you try to take some function, you have some unitary amplitude or unitary theory, and you try to do a continuous deformation, and then there will be non-unitarity, also which is non-hidden, like in the case of say evanescent operators, right? Like if you try to do continuous number of dimensions, or you could try to take like an ON model with continuous n, right? And you can get these operators with complex scaling dimensions that Igor dubbed spooky operators, right? So that's like the worst case scenario, but maybe we can also end on a slightly more upbeat note in that, when you construct these amplitudes from the bottom up, right, there's actually some degrees of freedom you have left over on how you define them. Because, these papers that constructing the amplitude, candidate amplitudes from the bottom up, right, they look at the poles, right? But if you look at any function at just, a discrete set of values, that doesn't fully specify the function, right? You could always imagine you add some extra periodic terms that, don't contribute at that discrete set of points, right? And so in the case of the Kuhn amplitude, you could imagine that you multiply it with some extra function like this, which, it's a quick check that on the poles, you get cancellations and don't change the amplitude. And indeed, these kind of periodic terms are indeed what we see cause the terms of this form are what cause the positivity violations in the first place. So it's possible that there may be a fix, right? But so the unitarity is so powerfully constraining, right? That if there's a fix, it pretty much has to uniquely specify the function and not leave us with any degrees of freedom left over. But so yeah. Hopefully in the near future it will be found out that there is such a fix, and if it's not found out, then probably over the next reasonable amount of time, then probably there isn't a fix. So we'll see what turns out to be the case. In any event, thank you for your attention.
Vision. the fact that this amplitude is not very wanted. The sun amplitude was supposed to be 3 level up. It is a 3 level amplitude. And here there is a branch cap, so it's not a 3 level amplitude. Let's say it was positive. How is it going to think about it?
Well, yeah, I mean, the hope would be that then it could point to some new physics. The one with multi-scalar. Yeah, it's this is the brain picture with scattering in ADS. Right. Yeah. I mean, because it's certainly the asymptotic behavior, right? Where you have like where it's like, I guess it's like log A is some negative number, right? And then log S, log T, right? So, I mean, the exact amplitude hasn't been reproduced, but at least this asymptotic behavior, right, does exist for what is definitely.
What people call part of
Yeah.
There is no pole. Just imagining some interpretation, right? Because normally you would say that the imaginary problem dissociates and it's like what they were saying is that there is NG's refrain when you separate out one. Yeah, right. So the dissociation has to do with making. So there is the immediate states, right? Right, but then kind of the entire simulation there as well, right? But imagine function. So this modification that was in the second whole paper, it was just yes.
I think so. Yeah. Yeah. I mean,
saying this guess is not good enough.
Yes, that's right. Yeah. I mean, it's a bit similar. You know, Grant's last paper with Clever Chung, right? In a sense, they also introduced this prefactor by hand, and indeed, like specifically say that like they are open, like there could be more extra ways of like extra degrees of freedom in what you choose for your prefactor.
You look at the terms can we interpret those terms?
Yeah.
Was that part of the cut?
Right, and I guess the same with this this possible proposed like this possible fix with these extra. Yeah. So this I purely noticed on a mathematical level. I don't have any physical intuition or reasoning for why you would have these extra.
Since those type of states, right? This mathematics and then it could be negative. I mean, so it could be interpretation involving states.
Right. I mean, I guess the hope is that you won't need any other physical states at all, right? If you find the right expression, that's the hope at least.
The sum theories that we find
So which of them? This like BN? I'm just checking out. You're asking about this sum that was like BN sine. Yeah. So this one. Yeah. But basically, these coefficients decay exponentially. So it is. I mean, it is this sum that is convergent. Yes. Yeah. Yeah, in principle, you know, there's also, you know, when you do this forward limit checks, right? There are some subtleties, right? Because, for example, in principle, I omitted the slide with the technical details, but you're different. You know, you're commuting a differential operator when you take the forward limit, right? You're differentiating the Gegenbauer, so you're commuting an infinite sum with a differential operator. right? And that's only valid when you have absolute convergence, right? But you can check numerically that you do have absolute convergence. It is justified to perform this commutation. Yeah.
Checking the poll, that obviously the other fossil channels cannot possibly increase the emission.
Right, you're saying adding together. No, I don't think it's obvious. It is, I think it hasn't been explored or like ruled out as a possible loophole.
Features because SMT seem
Yes, yes.
What about future?
Right, yeah. So for an actual amplitude, you need to add together, you know, you would have the amplitude as a function of S and T and then add together S and U and T and U. You'd have to add the full sum together. Yes, that's right.
So it's this way future is okay.
And
No, I mean, because like Raymond was talking about of him, if this going to future very much additional constraints.
okay, yeah, I think, I mean, in this case, if you could say that like the imposing unitarity at a partial amplitude is more restrictive. So in one sense, it's like almost the requirement here is too restrictive that we're just looking at a simple channel. But if the single channel does satisfy, then the sum will satisfy. Yeah.
Great.
Great work. I have only one correction.
Oh,
I think it's pronounced Reggie.
Reggie. Oh,
you can
it's a soft G.
Yeah, Reggie. Yeah.
Is this it's Italian? Italian?
yeah.
Okay, I see. Yeah, so you're saying I could double check with the Italian. No, I'm sure you have the right. I'm sure you have it right.
Sorry, so we have coffee after.
Because reggae means.
Yes.
No, you'll be giving many talks on this. I don't have it more.
Yeah. No, thank you. Yeah, I definitely don't want to keep mentioning reggae.
What's the South Park thing?
It's Eric Cartman has the superhero called superhero alter ego called the Coon.
Oh, I see. I see.
I'm so sorry.
Sorry. Microphone.
Oh, I don't want to steal that. Don't want to run off for this one.
like this, and now it's on, and you can put this in a pocket or something if you like. Yeah. You don't have to clip it unless you want. You could just put it in a pocket. Up to you. It doesn't seem to interfere much with keys or.
Okay. Oh, there's a long one.
Yeah. Defend yourself.
Okay. And I just,
Oh, for advancing slides, I would say the easiest is just use your arrow key or just click. or something.
yeah.
You don't have a clicker. Let me try to get more. Come back.
I never.
The only Christian is out there, he's coming back in.
Yeah, that's great. That's great. Thank you. And thank you to the organizers for inviting me to this great workshop. I learned a lot. And I thank everyone I've been talking to who has presented interesting talks here. So it's a bit of a new field to me, so I'm learning and learning. Even this project here I'm going to talk about is sort of a new direction for me. So bear with me. Okay. This is about gauge theory, of course. I don't really have that much to say about confinement yet, perhaps later, but not in this talk. But where I'm situated in a diagram of adjoint matter gauge theories is down here, right? No, because it's just scale. This is the number of scalars, adjoint scalars, and the number of adjoint fermions. N equals 4, super Young-Mills is here in the middle. It's a beautiful theory, although it's perhaps not what we are most interested in here today in this workshop. But to learn about these theories and what properties they have is sort of a general question. And there are some interesting relationships here which are a bit surprising. Now, focusing on this part will get us into the problem of not just looking at the couplings of the gauge couplings, but also scalar couplings, interactions of scalars. What can that do to the properties of the theories? So why do I want to look at this? No fermions. It's actually started, well, it started with an attempt to do holography, but then I found a curious old question about just Young-Mills and bosonic strings, which was apparently sort of left hanging. There was no, there may be reasons for that. Why would you worry about bosonic strings at all and the relation to Young-Mills? It is curious though, and I had the tools to look at it, so I started looking at it. Now, in the process, we rediscovered, should say that's this work is together with an excellent grad student. we discovered a way of doing the calculation. Just it was just a tool for us in the beginning, but it was an algebra that has strange properties, and it seemed to be surprisingly powerful to us. And I will talk about that. That may be more of more interest than the particular model can be generalized. It was a rediscovery when we put the preprint on the archive. I got a mail from Hugh Osborne, so we recognize this algebra. And some of you may also recognize it. But I'll come to that later on. It hasn't been overused, I should say. Maybe there's a reason for that. For the moment, I think there is no reason to not use. You should really look at this algebra. It seems to have interesting properties, but the jury is still out. Okay, what was this curious issue about scalar adjoint gauge theory? Looking at the beta function, say we have m adjoint scalars. The beta functions for Yang-Mills coupling takes that form. I'm written it in a large N format because many of the things I do will be simpler and more natural in large N. This relation, of course, doesn't make much of a difference. What's curious about this is that 22 adjoint scalars you get that from dimensional reduction of bosonic, just ordinary Yang-Mills in 26 dimensions. Of course, you don't really think that's the theory in 26 dimensions, but formally you could ask, what is this? Why would you start and get something at least on one loop level conformally invariant, the zero beta function? Why would you get that?
To make it 26.
To make it
26.
yeah, I mean, you get you get it right. That's and then why is this? I mean, that's as Igor says, it has this kind of theory has a sort of interpretation of as a low energy limit of a bosonic D brane. But this is nothing you would think about if you were just looking at it from a gauge theory perspective. It's a bit of a mystery from that perspective. And why would the gauge theory know about the critical dimension, which is of course 26 of a bosonic string? Why would it know about it, really? No, I mean, that's the significance of one loop is just that it's the first result that is independent of the interactions. Of course, there are corrections. There are, of course, the theory in bosonic string theory is not a well-behaved theory either. So you have to have corrections, there are tachyons, etc. So your point is, of course, valid. This is an observation. In the end, you have to some higher loop diagrams as well. But even this observation is, it's a bit curious. You could also ask if you ask certain questions in bosonic string theory, you can forget about tachyons and other thicknesses of the theory do not have any influence. Are there similar questions in Yang-Mills theory? Is there a way of taking limits, etc., that makes it a more self-contained theory. This is something that I can study, right? It's a question. I mean, there are higher loop amplitudes or higher loop corrections, of course, in beta function. But as yet, you know, because
discrete. So it is an exponent. Exactly something that the beta function is exactly. Have one parameter.
yeah, no, I mean, I agree completely. It's a curiosity. It is a curiosity. But you know, I'm curious. That's it. And there may be something here, and we don't know. I mean, I didn't. Oh, yeah. Yeah. I mean, okay. There is a quartic interaction. It's this commutator squared thing. If you just take the classical action for the, was that what you're asking? What the?
What you're gonna tell us.
Oh yeah, I'm going to do it. Yeah. That's fine. All right. This is just you know, whatever perspective you want to have on this work. Is anything that works for you is fine. Otherwise, you can decouple. Except perhaps the algebra. That may be something that is a more general interest. Let's see. Okay, so I will talk about beta functions. It will here in this talk just be about one loop. But of course, I'm worried about higher loops. That's you know, outlook, and I've some you know, some ideas about them. Then I'm going to talk about algebras. You say that I could call them marginal algebras because they have the elements in the algebras are marginal couplings. The old reference is to Michel and Radicati. They found this a long time ago. These algebras, originally not to do with renormalization. In the common work, Michel later went on to discuss how it works in scalar theories without gauge interactions. We call these diamond products, the products in the algebras. They called it V products. I just kept the notation because, you know, we didn't know about the old use before we published the paper. And then I will tell you about the actual results for the models. So how do these models actually behave? All right. So this is the model. Gauge interactions, minimal coupling to scalars, and quartic couplings. I only care about the quartic couplings here. And notation, there are two different ways of writing this. This is the more convenient way of writing in terms of matrices in the Lie algebra, and the A index is the index of the scalar, what scalar multiplet we're in. And these are supposed to be all the quartic interaction terms. And we're written down like this in this language. This form of the quartic interaction, the potential, is going to match with, you know, if we want to take results on beta functions from the literature, just sums over scalar fields with all the indices combined into a multi-index like this, and this would be the couplings. There are certain couplings here that correspond to the coefficients of these four invariant possible quartic interactions. Okay, so that's the model. Then, yeah, It's a simple X. This is a very basic talk, right? You see it, it's just the perturbation theory. There will be, for the one loop beta functions of the scalar couplings. We already dealt with the one loop of the gauge coupling. For the scalar couplings, there will be contributions from repeated quartic interactions. There will be external leg corrections and these double exchanges, purely gauge particle induced. This term is the one we're going to be most interested in. These other terms are we can add on at the end. This is where the algebra sits. It's just, you can see that it's sort of a square in a sense of the coupling, right? So that can be thought of as an algebra in some way. So this sum we take to define a commutative product like this. It's just the definition. It can be written in terms of a more ordinary product, just product of matrices in sort of the two particle space, like this. But you still have to sum over all the permutations. That, of course, came from the permutations of all these diagrams. Oops, I'm just going to go like that. Now the product is distributive, and then this means that this product is what's mathematically called an algebra. It's a bit curious because it's commutative, but in contrast to this, just the ordinary matrix product is not associative, right? So it's a bit unfamiliar. But that's just what life, that's what it is. Here's, oops. It still appears. Still appears. It still appears in the beta function. It's obviously something that is of some physical interest, written in a strange way, but we have it there. The last two lines here is more for higher loop considerations. It's you can skip it for the moment. So there's a lot of information in this algebra. You can extract a lot of things about the RG flow. There are also sort of experimental signs that there is more to it than just what I'll show you directly. I'll just indicate it. And I said they are known from, the first paper on this kind of algebra is in physics is this from 71. Michel went back in 81 and discussed this in the context of renormalization. So, if it hasn't been used for that long time, maybe it's nothing to worry about, but I'll show you what I find, and I think it's intriguing. Any case, okay, in algebra, it's a linear space. You can choose a basis for it. The basis, conveniently in our case, would be to be the actual invariant couplings that I showed you, the four ones. In other theories, there would be different bases. So you can just decompose it like this in terms of the basis element. Beta functions will have a similar decomposition, and the components of the beta function can also be written. The full beta function equations can be written in terms of structure constants of this commutative, non-associative algebra. And they all can be extracted from this product, right? So now the task is to do this and then just get the beta functions. And then just look for the RG flow. Okay, this is a repeat of the notation. These are the objects of interest. You can notice that there are sort of 2 single trace operators and 2 double trace operators. They have will have different properties. We'll see that very clearly when we look at the algebra. All right, lots of now you can see here how efficient it is to write things in terms of polynomial. If instead you wanted to look at the tensor structure that contracts these scalar fields, they are here, right? For the 4 different invariant couplings, right? But these are interesting because we need them to do the contractions that enter in the beta function. They will also tell us about the algebra. All right. So here, for example, you have this single trace operator. It's a tree-level thing. I wrote it in terms of a kind of notation which is about similar to what's done in tensor models, connecting different. You have to keep track of all the indices and how they're contracted with each other in these different terms. And here they are. The blue lines are supposed to be the SUN indices in the adjoint, and the black lines are just the Kronecker deltas in the space, so the sort of a flavor space of these scalars, like this. If you then, this was starting from this, one of the invariants written down in terms of these diagrams. You can write all of them in terms of different topologies of these diagrams. You see clearly, the double trace nature of the last 2 by having just their disjoint parts to it, to the gauge structure. So then you just have to multiply these together. You can do that in some sort of diagrammatic bird track language or just using algebra. Eventually you get this summary, which is the algebra. Diamond products of these 2 elements give you this sum of elements. That's what an algebra is. You can check for yourself. If you don't do it in your head, you can work a little bit and you see that it's going to be non-associative in general. Curious, but that's it. I grouped the products in a certain manner here, but this is of course too complicated to digest. It's a bit simpler if you take the large n limit and define large n algebra elements, basis elements. Simplifies considerably. So what was done here? It's sort of a contraction of the algebra, similar to contractions of Lie algebras. I rescale coupling constants and tensor structures in this way, preserving the product like this. And then I make sure that the products, the structure constants do not diverge. Then I can get the reasonable, interesting contraction of the algebra. And to do that, I find that I have to do a scaling, which is precisely the ordinary 2 scaling of this kind of theories with single trace and double trace operators. So the algebra tells me about this. This is the way to do it. Interestingly, there are other possible large n limits This is the standard one. If I also allow M to grow, I get some sort of Veneziano-like limits. And the consistent ways of doing that, getting a finite structure constants, picks out particular Veneziano-like limits that are actually closely related to melonic limits that appear in tensor models, which I find intriguing. This is one of the sort of signs that this algebra summarizes something very important to us, for whatever that's worth. Now, you can also read off interesting things about the renormalization group flow. Of course, you can, because they summarize the renormalization to one loop order at least. The subalgebra is just a set of part of the algebra that closes. You can look at this three-dimensional subalgebra or that one-dimensional subalgebra. And say if you put all the other couplings to 0, you will, if those products close, you will stay in the subalgebra. So you will have closed renormalization group flows in these subsets of the space of couplings. That is, if it was not for the gauge coupling, which induces certain flows that can take you out of the subalgebra. But there is a more interesting structure, even more interesting than subalgebras, which is you combine the fact of being a subalgebra with something more. What would that be? Well, in algebras, there's a notion of an ideal, which is, it's also subalgebra, but has the added benefit of if you multiply an element of the ideal with any other element, it will stay in the ideal, the algebra ideal. If you do that, you can also define sort of a quotient algebra, and which is the sort of transfers to the subalgebra, and those, because of the fact that it's an ideal, you will find that those RG flows in the quotients, they will be independent of the couplings that are in the ideals. It's sort of a it's a semi-direct products in some way. So you simplify this set of couplings have a independent dynamical system in the renormalization group flow. And the others still have, the ones in the ideal also have some interesting properties. They're just subalgebras like the previous slide. But the fact that this is sort of isolating parts of the flow gives a hierarchic structure to the flow. It will give a hierarchic structure also to the set of fixed points, if you can find any. This is the whole set in the large n limit of the beta functions of these couplings mu that are scaled with the gauge coupling, right? Sometimes it's called fixed flows. The flows of these couplings, and if there are fixed points of these flows, they're fixed point of these RG equations, they are fixed flows. They will be roots of systems of second order polynomials. Here, I just have to admit that it's not very beautiful. This is the result, in a sense, a summary of the result, I would say. You can see the gauge coupling, how it behaves, depending on M, and the single trace couplings and the double trace couplings. Lots of different special cases. Fortunately, this hierarchical structure helps. And let's see, I kind of focus on something part of this picture. It turns out that there are no true fixed points, which sort of I hope to find fixed points that would be interesting. It would be defined conformal field theories, but in hindsight, you shouldn't have expected that. This would be the real fixed point. If here you would have if you had fixed points for the scalar couplings here, it would be a true fixed point for all couplings, a real conformal field theory. Doesn't happen. What happens to the flows of the scalar couplings as you increase m? Well, this is a hierarchical structure. Eventually here, what I've listed is, I thought, when do these theories make any sort of sense as in some limit, because you're already forced, if you're interested in fixed points, you're how should I say, if you're interested in these fixed points, you're forced by the structure to look at large m, and then the gauge coupling is IR free rather than UV free. So then I thought maybe it's interesting to look at what the possible structure is in the IR of these theories. And I listed cases where you have complete perturbative fixed points in the IR. There's no one that is completely stable, but there's one unstable directions for the green ones and two for the what we call cyan colored ones. For what that's worth, all of these have unstable directions, but you can, if you wish, sit on a fixed point. For the structure, you can plot what happens for various values of m. This is the single trace flows where m is large enough that you will actually have fixed points. There's one UV stable, one and one saddle. At those values of the single trace couplings, you can look at the flows of the double trace couplings, and there's actually a set of fixed points there too. This is a coarse grain view. You can look closer at that, and you will find that these are actually is a long, narrow parallelogram, which if you look closely in this region, it separates into a saddle and IR stable fixed point. And the one below separates into UV stable and the saddle. This means that you could have in the IR theories that sit here and stay there, so they are perturbative. Oops. What did I do? That is, yeah, this is the example what happens for when you don't have fixed point. You have flows like this that go from the if you start, this is towards the UV and this in the IR. If you look at the IR, like that was sort of indicated the other diagrams. If you start out here for negative values of couplings, you would expect to have, and you can follow that through, that you would have Coleman-Weinberg radiative symmetry breaking. And then, of course, you would have to study again what happens if you wanted to. For us, I suppose it's time to close. And what to do next? here. There are a few exceptional cases that we haven't covered yet. The simple case of m equals 1 is not included actually because these 4 quartic couplings are linearly dependent in that case. So it's just a matter of checking it, but I haven't done it. Then finite n, most of the things I showed you were for large n. There could be interesting stuff at finite n, who knows. Higher loops, as was mentioned, obviously. But I do think it is interesting that what the algebra sort of indicates to us, that there are specific limits that have very nice properties. They are sort of singled out by the algebra, and we don't know yet all the things that this algebra can do in this system and in others. So that's where we are right now. Thank you. Some point what? No, that's I mean, they do diverge, but they don't actually bifurcate. It's if you go to higher resolution, it's sort of unique. Oh wait, I see. Let me think what you mean. Well, it takes that direction. Yeah. I suppose you can, if you take it as a flow from minus infinity to plus infinity, it will go either on one side or not. There will be lines in between. It's continuous in a way. Yeah. No, I wouldn't call it exactly bifurcation, but it's similar. Yes. Yeah. Yeah. I don't. Yeah, I mean, you do scale in a different way, so it is precisely as you say. Well, that's what you would think, but you could scale away that in principle. I'm not saying this is going to happen, but you can scale that. Those terms in the beta functions to 0. It could happen, and that would be super interesting, of course. But it doesn't look like it happens in a simple way. It could still happen in a complicated way, but we are exploring that. Yeah, of course we are. Yeah. Yeah, that was the starting point. I mean, I'm actually not that interested in that any longer. It also looks like I mean, who knows? But yeah, I mean, there are. If you take a Veneziano-like limit, large M, it is like a large dimension limit of D-branes, and you could think about large dimension limits of gravity and things like that. But and if you say, if you want that is related to some sort of string theory or not, I still, yeah, I mean, the higher loop question for M equals 26 is, of course, important to check. It doesn't look promising, but, we're also checking that.
That you had some kind of OM symmetry in both.
Yes, yeah, I didn't emphasize that, but I mean yeah. I mean, this is
otherwise number of couplings will explode, right?
Of course. Yeah, I mean, it's you could investigate symmetry. You can always have a cascade of symmetry breaking from these But that, I think you would find that if you started from the symmetric ones, you would find that going further and further down. Yeah.
Very good. You might want to-
Yeah,
you might-
that's right.
Broadcast it.
Yeah. I can both detach it and.
Yes.
Please save the battery.
Then it was off. But
Voice is so clear.
that's okay. No, it's not. Well, okay, you can do it indeed on a massless limit, but then you make Lorentz invariance very non-manifest. But okay, yes, let's. So this massless limit is not reality. So as I say next, so there's a problem. Okay. So there is only some approximate cancellation, and in particular, we cannot really do a useful field redefinition. So our effective field theory and moreover, mass of the axion is of order the string tension. Okay, and our effective theory breaks down at energies bigger than this. So is it even a sensible limit in any sense, or am I just doing some pure numerology? Okay, so to support that it's not pure numerology, let me explain to you some results, some update, some old and new results on worldsheet S matrix boost. Okay, so punchline is the following: the older result of this very nice paper is that Bootstrap also finds the axion of comparable mass and with coupling also very close to this critical coupling. Okay, and then update is that this physical mass of the axion is light. Okay, to the extent that Bootstrap results do not change much if we take MA to 0. Okay, so it's some way of making kind of Bootstrap, I'd say, is a bit more rigorous way of doing some naive dimensional analysis, putting some factors of 2 pi in the place and saying that this mass is actually a light particle. Okay, even though naively it doesn't seem so. I'll explain in a moment. Yeah. Okay, that was punchline. I mean, then now let me say what I mean by this phrase. Okay, just to tell you what you should anticipate on this discussion. Okay. So we use effective action without. So what does Bootstrap do? So we use effective action without axion. Okay, so axion is not put in, but with some non-universal terms included with like arbitrary coefficient. Okay. So first non-universal terms and Bootstrap studies 2-to-2 scattering. So then the amplitude leading corrections to the amplitude are parameterized by these numbers alpha 3 and beta 3. For example, the log of the amplitude in anti-symmetric channel, it depends. Okay, that's the leading piece. That's the one loop piece. Remember, this alpha 2 is this d minus 26 term. And then that's what related to particle production, but it's its avatar in the 2-to-2 amplitude. And then there is some combination of alpha 3 and beta 3 that appears at Maxwell. So then what Bootstrap does, they use crossing and unitarity to constrain alpha 3 and beta 3, and then, okay, look close to the boundary. So this look close to the boundary thing is in green because constraints are rigorous, but the idea that you need to look close to the boundary, that is a little bit inspired by some success of conformal Bootstrap, etc., where you find some physical theories on the boundary. So we can discuss how to justify it, but for now let's just do it. Okay, and that is what's happening. So I'll guide you a little bit through this plot. So you see, this is this alpha 3 beta 3 plane. So everything in white is excluded. So theory must live in this gray region, and that is rigorous. So now there are two boundaries. Okay, and if we look at the boundary where beta 3 is positive, then there is one sharp resonance. Okay, and now we look near the boundaries. So near that boundary is one sharp resonance, who is a pseudoscalar, so it has the quantum numbers of the axion. And here, as we move along this boundary, the mass of this guy moves. You see the color coding from blue to red, it moves from blue to red, and then like 1.5. Okay, that's somewhere here, so it belongs to the plot. And moreover, now if we look at the coupling, then coupling for all this range of masses, and especially when we go to mass something like 1.5, it almost is not changing. Okay, it's converged to this value, and this dashed line is that critical coupling. Okay, so these are the numerical results, and this is what I mean, that MA corresponds to MA 1.5 already corresponds to large beta 3, because from the point that corresponds to this mass to beta 3 going to infinity, pattern of resonances and say couplings of this resonance basically does not change. Okay, so in this sense, Bootstrap already converged to a massless MA limit when we take the physical mass, right? So that's sort of bootstrap allows us to study some theories that are not QCD, you know, some just maybe non-physical theories, but okay, they capture some infinite set of dispersion relations, right? So that is the point. So it's not just random non-physical theories. Good, and that basically then, as I show on the next slide, but what we did, we developed some scaling theory that tells us that the here physical value of beta 3, whatever, what appears in computation is some combination of beta 3 that even, you know, here like beta 3 is small, but really what appears in the counting is this combination, which is of order 20 for this value of beta 3 corresponding to MA. So you get some 5-ish% results within the massless axion limit. Okay, just very quickly because okay, I'm running out of time. So these results can be understood by using like a scaling theory of light axion, where basically all non-universal corrections of the action are dominated by integrating out the axion. And more or less this what bootstrap finds. Okay, and that would be justified if the axion was very light. Yeah, maybe. Okay, Andrea there is nodding approvingly, so he understands this much better. But yes, and as I said, so precise cancellation, and then so this cancellation of here we studied just 2 to 2, but there is a cancellation of 2 to 4 related to the cancellation of growth in the 2 to 2 amplitude. Okay, and then this precise cancellation bootstrap finds only beta 3 to infinity limits, but okay, for this value of beta 3 that we care about. And beta 3 is just related to the mass by some simple scaling formula. It already this happens. Okay, so sort of numerology got confirmed by bootstrap, and the justification for light axion limit was also provided by bootstrap. Okay, now let me review very quickly the BFKL. I'll probably skip Regge theory. So we would like, what's the point? We would like to UV complete the worldsheet effective theory by matching it to high-energy QCD. So that's the big goal. So now Regge theory is one potential way to set up such a connection. So let's consider high-energy scattering in QCD. So I'm taking the following order of limits. So as I said, n is the largest here, s I take large, much bigger than minus t, but t itself is 6, but bigger than lambda QCD. So in this limit, amplitude is given by a sum over some s to some power laws that depend on t. So these guys are the Regge trajectories. Okay. So now BFKL and some further developments is a tool to determine this alpha ends of t, and it is really controlled when the t is absolute value of t is larger than the QCD. So I'll just give you here the answer that this alpha ends are given by eigenvalues of certain differential, whatever, integral operator that acts on functions of R variables, okay, where of these R variables, we can think of the positions of so-called regions. There are some regions that are represented by these blue lines, and they live on two-dimensional planes. And then there is some operator that we need to diagonalize on this basis of functions of R variables, and that will give this set of Regge trajectories. So say leading order in lambda QCD that is small because I'm at large S and large T. This operator is given by a sum of pairwise interactions, where each pairwise interaction is this sort of relatively simple looking kernel. Okay, so that thing starts looking, especially in the limit of large number of regions, as some sort of spin chain, where at leading order we just have to nearest neighbor interactions, but then at higher order some more complicated interactions appear, and also this kernel gets modified. In the regime where we have control, so that 12 coupling is small, and again we're at large n, you see that this say the ground state of R equal to operator, that's what's called the Pomeroy trajectory, that's the leading Regge asymptotics in this region is given by this formula, where you see something interesting happens, that subleading correction there's a leading answer, the subleading correction is also computed, is proportional to the beta function. And it so happens that this leading kernel, it turns out to be an integrable system as well. But then the subleading correction, it breaks integrability. And note that there is also this thing that was mentioned in the talks just before, that this coefficient is, some 11/3, and you can add some, flavors to the theory. It will change in this form. It's the same coefficient as breaks integrability in our low energy stringy picture. So the hope here is that, okay, and this axion almost unitarized this particle production in the string picture. So the hope here is that, okay, maybe we can match our IR calculation to this UV calculation, okay, staying within a single string sector, because we're at large n and physics is, closed. Very single string sector, and that's what I say here. Could this be connected to UV integrability? This approximate integrability of BFKL, connected to this integrability of strings. So I remind you my big picture. So here we have T. Here we have the region of long rotating strings, and here we have BFKL. Okay, so according to Regge theory, these are connected by continuous Regge trajectories, and if alpha of t is analytic function, can we connect the two? Now, how much time do I have? 5 minutes. Okay, so I wanted to discuss a little bit, review the Regge theory, but okay, it's not worth in such a short amount of time. But there's an argument for why. You see, it's a non-trivial statement, right? It's not a trivial statement that positions of physical particles in T-channel scattering are connected to the asymptotics in the Regge limit, right? But that is at least for a meromorphic amplitude with which we're dealing here, it can be established. Okay, modulo some subtractions, assumptions about UV behavior, but that's what I wanted to review here. But I guess anyone can read Gribov's book. Sorry. Yeah, yes. You can read in Russian too. So. It's even better. So again, yes. So the punchline is that there is, I think, a justification for continuity of this Regge trajectories. There is a regime where we have control by using long rotating strings. So what I reviewed to you was the theory of long strings of type 1 and 2. But as also Gabriel mentioned, the bulk of the string of this long rotating string is the same as Arkady was asking, whether the worldsheet theory is the same. So there is also some approximate integrability that is related to these long rotating strings. Now, when T becomes small, string becomes shorter, we lose control. This blue region is we don't have control, and then there is a green region where we again have control, and we have this spin chain that is also integrable and kind of becomes non-integrable and strongly coupled when we go here. Yeah, these guys are Jezide gluons, these blue lines. Yeah. I'm skipping this derivation because it's complicated, the Romanian, but okay. So now, yeah, basically what I want to say, a real QCD trajectory, that is this red line that becomes something wiggly, maybe complicated here in the middle. Okay, but what we are looking for is some integrable approximation, okay, some imaginary integrable theory. That's this purple trajectory that matches well to real QCD, I mean, still large n, whatever, in this region, and that matches well to BFKL in this region, okay? And then we've seen some hints that these deviations from integrability, they are small and maybe even sort of smaller than expected by naive power counting in this region, right? That is what I reviewed in the beginning of the talk. Okay, good. So yeah, that is what I just said, and then we need to understand this approximate integrability for rotating strings. But it is something concrete that we can do, and what Gabriel and friends are working on. What I want to say is that also we have, I'm concluding basically. So it's good thing that we have ways to test how robust is this numerology of ours, these constellations, right? Because, for example, we can study theories with additional matter, right? And then we know how matter changes beta function, and if this axion coupling survives the integrability condition. And we also study theories in smaller dimensions, say this BFKL machinery can also be developed in 3 and 2 dimensions. And then this maybe will be even simpler examples where we can make some analytic progress. Okay, so using both lattice and analytic calculation. And then, my last slide is that, of course, the Regge limit is just, it's one of possible connections to of long strings to QCD. For example, if you remember Raju's talk, so he talked more about some quarks or whatever partons flying apart and emitting soft gluons in the middle. And then, so this, the distribution of very soft gluons over here at large n should also be described by the theory of long strings. So this kind of production of a string more in S channel, but this is a real string, while this BFKL is supposed to produce some sort of analytically continued string to negative energies. So anyway, this is what we're up to. So I'm hoping to report on the progress of this computations that we're doing in the future meetings. Thank you for. Well, yeah, we're trying to establish.
I remember it went down about the effect of this task.
Yeah.
I even heard from some people that it might take slow. It's gone away.
Well, I don't think, again, from effective theory, they cannot change the slope. They can give this correction that is j to 1/4 as opposed to linear j, so it's relative to j to the minus 3/4. But on the other hand, I should also maybe mention that there is some puzzle in 3 dimensions when we look at the lattice data. So there is a spectrum of blue balls. They seem to lie on a very linear trajectory, but the slope of that trajectory does not match this tension, that you would derive from effective string theory. So it is a puzzle. I don't know. I think it's very interesting to understand whether it is some lattice an artifact or it is something important that we're missing in this effective string theory. I don't think it can be, fundamentally wrong, but okay, maybe there is some big ingredient that we're missing, and that's something again that would be very surprising. But I think we have the tools to debug it, using lattice. We can more, I think, in principle, understand sort of the shape of these objects, and we can see, spend 6 glue ball, for example, how it looks on the lattice. You can more or less study it and see, what's wrong or what's right. So yeah, would be surprising, but also interesting if something is wrong with that picture at a basic level, right?
There, on the other hand, a very precise match quantum numbers, basically all of those people to the speech propagating string. All of those people, to each of them, can be just identify the situation. But then they slow the leader trajectory from get 30% forward. It is very hard. So I think there is some idea.
No, you told me some arguments why the cast may generate non-local terms.
So that I hope that maybe that was my calculation to start with because it's very slow.
Yeah, in principle, just to sort of speculate on if this works, then okay, this BFKL chain, there are some boundary conditions. So you create something that looks like an open thing, even though that's supposed to match to this global. So you should sort of recognize that there's some left moving and right moving sectors. And in principle, there is, there are some boundary effects over here. But yeah. Mm-hmm. I skimmed over it because I don't think there is an argument, and moreover, I'm not committing at all, to be honest, that the leading trajectory over here maps to leading trajectory over here. There are in principle even some reasons to believe that I think there are reasons to believe that at large n there will be some level crossings among these trajectories, and it is sort of the part of the problem is to actually identify. So here we have good control about a bunch of leading rigid trajectories. Not to complicate the picture, I drew them without any crossings because it's not something I'm certain about. But I'm not making a claim that it's really the pomeron that is continuously connected to the leading global spectrum. It would be true if there were no level crossings. But I think at large n, at infinite n, in a strict planar limit, we can actually expect some level crossings in this picture for some subtle reasons that we can discuss. So yeah, I'm not. This is very schematic. These points are put like at random. Okay. Lattice global is a scalar that we know from the date from lattice. Yes. So that in 4D and in 3D that happens to be the case, but there isn't, I think, a theoretical really. Arguments, yeah.
I have a question related to that. Can you imagine that if you change the matter content, you could make the lightest state?
Yeah, that is. I think it's really interesting to, again, the only way I know how to address this is lattice. Yeah, I don't know, maybe in particular in supersymmetric Yang-Mills. Yeah, in supersymmetric there should be some degeneracies, but okay, I think it's an interesting question. What happens if we add to our action, some adjoint fermions and some adjoint scalars? And
well, particularly,
mm-hmm.
You can get both of them.
So why is that? Why you get pseudoscalars?
So they're not pseudoscalars. Well, just because they're Carlson.
Yeah, but pions. Okay, good. I'm not sure if pions. So here it's true. We should see pions on this plot, but I do not know, for example, how this will manifest itself on the string worldsheet. I think that's an interesting question. Like, do we see anything special on the string worldsheet if we have, let's say, some chiral symmetry breaking?
The model of Thomas, the Thomas model has CP1. But I'm saying the gap is not in the box, so
yeah, you see, if it, yeah. Well, at large n, the point is that at large n they decouple. Yeah, I think that will not invalidate the argument. But whether you get some, sometimes people propose some interesting sigma models on the worldsheet, but that, of course, you expect it to get gap because it's two-dimensional theory, some 2D sigma model. But I mean, in supersymmetric theory, of course, we expect some Galstinas on the worldsheet. That's a very sharp prediction. Then if we have, some fermions that are massive by light, you expect some light fermions. Okay, if you have some scalars in the bulk, you also expect the scalars to incorporate into the string. That's what I meant by this light comment. So you can tune and produce some other light scalars on the string, and they will run in this loop. And you can see if our formula for the axion coupling, if it follows the same pattern as the beta function, right? So I had this this formula, and if we add some scalars, they add to this -5, right? And then the question if the logic continues to hold.
Time for
everyone. So I would say very inspiring meeting. I think it's a good start for theories and that.